The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar. My name is Trish Kerin and I'm the Director of the IQME Safety Centre. The topic for today's webinar is the human side of process safety. So I'm going to go through some slides and talk about some concepts and ideas and cover off some case studies in this. If you have any questions, please put them in the questions box and I will get to them at the end of the session. You can also use the chat box if you just want to share a message with someone else or add anything to the conversation as we go along. I will be monitoring both of those boxes towards the end of the session so that we can cover off on all those comments and questions. So thank you very much for joining me today. The human side of process safety, I think, is a really fascinating topic to delve into. It's important to really think about what the human side means. And if we refer to the safety centre framework that we talk about, where we've got leadership as one of the key central elements of process safety, and that leadership being exerted over a range of different aspects in the business, such as systems and procedures, engineering and design, assurance, knowledge and competence, human factors and culture. Whilst human factors appears there as one of those elements, the human is involved in every one of these elements. So we can talk about the detail in the engineering and design part, and that's where we do our detailed risk assessments, quantitative analysis, some very specific detailed design aspects of process safety. Every other part is very clearly, predominantly about the human. And so that's why I think it's so important to really engage in the human side a little bit more and understand a bit more about it. So that's what we're hopefully going to do today. Now, making sense of humans. I absolutely love this quote by Trevor Kletz. For a long time, people were saying that most incidents were due to human error. And this is true in a sense, but it's not very helpful. It's a bit like saying that falls are due to gravity. Humans will always be involved in what goes on in what we do. However, it's interesting to also think about the fact that humans are also critical so often to us getting it right. So it's not just about human error that we need to think about when it comes to the human side. There's all sorts of elements to do with, that moment that human intervened and prevented the incident happening because the system failed, the procedure failed, the equipment failed. Humans, most of the time, actually prevent the incident occurring rather than cause the incident to occur. Obviously, there are instances where we make errors as a human, and that can have an impact as well. But they are far fewer than the actual number of times that a human gets it right, because most of the time things don't go wrong. So obviously the human is getting it right most of the time. So what I want to focus today on is really about this idea of normalization of deviance. So we adapt to our environment and become very used to what we see. Now, this also brings in the idea of many of the different cognitive biases that exist, and psychologists have spent a long time studying cognitive bias, and I wouldn't suggest that I know that much about it, given I'm not a psychologist. However, there's some parts of it that can be really clear in what's going on. Things like confirmation bias, and that really is quite closely related to normalization of deviance. That says that I'm always going to look for the data that's going to validate what I have already assumed is the case. And so confirmation bias appears in a lot of normalization of deviance issues. It's a very interesting area to explore. Obviously, there are other parts of human factors as well. Ergonomic aspects of human factors is very important. The human-machine interface is very important. These are all clearly part of human factors elements. What we're just going to talk about today, though, is I'm going to focus us in on normalization of deviance and go through a few different case studies and examples of where we can really show that normalization of deviance had a lot to do with the incident that actually occurred. So what is normalization of deviance then? I think Diane Vaughan summed it up best in her work. So the social normalization of deviance means that people within the organization become so much accustomed to the deviant behavior that they don't consider it as deviant, despite the fact that they far exceeded their own rules for the elementary safety. So this is this idea that we start to drift in what we see. If we see it every day, we start to stop noticing it. So things like an alarm that is constantly there, and it is always about, it's always a false alarm. We're going to start to ignore it and not even notice it potentially. If we've got our plant operating within its normal operating parameters, but it moves from being in the mid-range to being towards the higher end of its parameter, that might be a deviance that we fail to notice because it happens slowly over time. And all of a sudden, we're at the point where we have the plant operating in a different way. It might still be operating within its normal operating envelope, though. So that's an interesting aspect too. Is it really a problem? Is normalization of deviance always a problem? Sometimes it may be, sometimes it may not be. So we're going to use this sort of definition as we go through and look at a couple of different incidents that have occurred and what some of the aspects were that led to those as examples. So the first one I want to discuss is the Columbia Space Shuttle. So this occurred on February 1st, 2003, so 17 and a half years ago. The Space Shuttle Columbia was on mission STS-107, and it broke up upon re-entry into the atmosphere after its mission was completed. All 7 astronauts died in that re-entry incident. Now, during the launch of that shuttle, the leading edge of the left wing was struck by debris that came off the external tank as it separated from the shuttle itself. Now that damaged, that debris strike damaged what they called the reinforced carbon-carbon coating, which was on the wing. Now that coating was there to provide thermal protection for the leading edge wing for the very act of re-entry into the atmosphere when excessive temperatures are generated due to the friction. Now, what's interesting here is that debris strikes had happened on almost every launch. They were a normal event. There was an issue originally when they started to have the debris strikes that they thought it was a problem, so they tried to look at how they could fix where the external tank was connected. They also looked at how they could work out how to reattach some of the reinforced carbon-carbon tiles if they needed to, whilst the orbiter was in orbit. However, they didn't ever manage to figure out a way to reattach the tiles whilst the shuttle was still in orbit. So it became an issue they just had to fix upon landing because everything landed the first time. So they hadn't actually lost a shuttle on re-entry. There were certainly 14 flights that had significant damage after or had major foam loss occurring. So one of the interesting ones, though, occurred back in 1988, and this one was actually Atlantis, I believe. Now, the debris actually knocked off a tile in that launch. When Atlantis landed, it actually did manage to land, although the wing did suffer some damage, but not enough to cause a complete burn through. That was actually discovered that the precise location of where the damage had occurred allowed it to survive the temperatures because there was an extra thick piece of metal in that particular part of the wing strut. So that extra thickness meant that it took longer for the burn through to occur. And that was how they landed. Now, you'd have to sort of then start to wonder, well, if that is a problem and we only just managed to land a shuttle, why wasn't there enough concern about it? But then as you can see through the rest of this list, many launches suffered impact damage and damage to the thermal events. But it was started to be considered an acceptable risk to them. They started to look at what was in the experience base, so they knew that regular strikes occurred and there hadn't been a problem. In this way, to a certain extent, they almost turned the story of a failure into stories of success because they kept landing the shuttles. Therefore, they could really achieve anything with this vessel. That was what they thought. Obviously, until Columbia was struck on January 16th in 2003. So they certainly had a history of the design issues. As I've mentioned, they tried to develop a repair strategy in orbit, but it didn't work. They could not actually make it function, the repair strategy. So they came to the conclusion that debris strikes were pretty much going to happen and the thermal protection should be okay. The leading edge was much harder in its thermal protection than the underside of the wing. So if it did get struck, it should survive quite a lot better than if the underside of the wing was struck, for example. The underside wouldn't be exposed to as much extreme heat either. So this just explains the photo of how they actually attached. So we've got these bipod ramps here, which is how the external tank is attached to the orbiter. What occurred is some insulation foam broke off from this bipod ramp and flowed down and hit the leading edge of this left wing. And that's what actually caused the damage that led to the particular incident in this case. So there's a whole lot of different factors that led up to this becoming normalised, and some of it goes right back to the original design program for the shuttle. So back in 1972 was when NASA decided it wanted a reusable shuttle to use after the Apollo missions and following the success that had there. And the original design scope was that there would be 50 flights per year, and it would literally be like the bus to get to space. And it would be carrying all sorts of different freight and cargo and people to the space station when that became an idea as well. But by 1989, it was only launching 24 times a year, and it was costing a lot more than anybody ever thought it would cost. So from the very beginning, it was not working to schedule, and it was well over cost. So this started to create a lot of pressure about maintaining flight schedules to try and get to that target of 50. And that led to them accepting lower specification performance because the previous deviations had not caused an issue. They had not lost a shuttle in the previous deviations due to foam loss. They had lost a shuttle, which I'll talk about in a few moments as well, before this though. So the shuttle that they had lost previously was on January 28, 1986. So it wasn't all that long into their whole shuttle program. And the Space Shuttle Challenger exploded 73 seconds after launch in this particular instance. The investigation found the immediate cause was the failure of an O-ring on the solid rocket booster due to the extremely low ambient temperature at launch. Broader investigation had found, though, that the engineers had actually recommended against the launch that day because they were concerned about the temperature and the fact that in lower temperature they started to see some blow past of those O-rings. So they were concerned about the O-rings holding during an even lower temperature event. But they were overruled by the organisation collectively, and the launch went ahead, as we know. The NASA culture here had gradually begun to accept the escalating risk of blow-by through the O-rings on the solid rocket boosters. And so it was perceived at the management level of not actually being a problem because previously there were 2 O-rings anyway. They only ever got blow past on the first one. The second one had always held, therefore it shouldn't be a problem. So following the Challenger incident, NASA made several changes to their organisational structure to try and address the cultural issues, though interestingly they didn't change the way they handled the human flight area, which was effectively where the incident had occurred, so that seemed a little bit unusual. So the Challenger incident, coupled with the cultural impacts that were happening in NASA, meant that by the time Columbia came around, this was an organisation that was focused on achieving whatever it could to get the shuttle into space because of the constraints they had on schedule and budget, and assuming that because an incident hadn't happened before in that way, that it wasn't going to happen. And so this was a significant issue that they actually had. And if you read both the Challenger Presidential Board of Inquiry and the Columbia Presidential Board of Inquiry, you'll actually find some of the cultural findings and the systemic findings very, very similar. It all did come down to accepting that increased level of risk and not actually seeing it as an increased level of risk over time. The technical issues are obviously quite different. One was foam strike off the bipod onto the leading wing, and the other one was a brittle O-ring due to excessive low temperature. But the cultural, the systemic findings are very, very similar in these two incidents. So one of the issues they had was that the design requirement originally was that there would be no debris shed when the external tank detached. But there was a history of strikes. So they got used to the strikes. It should be noted that Columbia's inaugural flight, and Columbia was the first shuttle ever launched into space, sustained damage and required more than 300 tiles to be replaced after its first flight. So there was certainly a big issue in terms of the impact. But they got through flight one and it landed intact with no risk of burn through. So the risk was then accepted that it wasn't really a problem here. So as I've said, they in the end got to the point, they normalised that there was no safety of flight issue. It was an acceptable risk for the orbiter to be struck, even though there were several instances of where significant strikes occurred. There's another little side part of the Columbia investigation as well, that because Columbia was actually the first orbiter to be launched into space, it had a series of other instrumentation installed on it because they wanted to measure all sorts of things on that first flight. So the Columbia shuttle was actually different to all of the other shuttles. When they built the other shuttles, they didn't build as much instrumentation into them because they'd had some testing and ability to see what was going on in Columbia. But they didn't ever take out all of that instrumentation. So interestingly, it was still giving readings at times, and those readings were often assumed to be false readings because it was never maintained. Those parts weren't important, so they weren't maintained. They started to get a lot of strange readings in the control room as Columbia started to experience its burn-through event and subsequent breakup. And they didn't know what to make of those readings because they had always previously been treated as false alarms. So there's also a lesson here around what do we do with equipment that we have installed on our facilities. If we're not relying on it anymore, is it still there? Is it still being maintained? And could it provide misleading or useful information at some point into the future? How will people respond if they start to see that? Again, this is all about that human impact, that normalization of deviance on what people are seeing. As I said, it was Atlantis that had that 1988 strike where Atlantis almost didn't land. Interestingly, they did actually have a camera on board Atlantis at the time, and Mission Control asked them to take a look at the wing, and the commander said it looked like it had been blasted with a shotgun. There was so much damage to the Atlantis leading edge wing. Yet it made it back into the atmosphere. This is an example of some of the damage that you can see. So this is a photo of Atlantis after her final mission when she was retired, and you can see that there's the main part of that tile is actually missing. I had the opportunity to see Atlantis personally up close a few years ago whilst I was in the US. It is on display, and it was quite interesting to see some of the tile damage that was there after that final mission even. So it was interesting in this whole process that they do have a launch review process. So after every launch is undertaken, a group of engineers and specialists review all of the data to see if there's any abnormalities. And they detected that there had been a substantial debris strike, and it occurred somewhere near the reinforced carbon-carbon panels, and that it was quite a large piece of foam and was travelling at quite a substantial speed when it actually hit. They were concerned about damage, and they made several requests for images to be taken of the shuttle, but they bypassed all of the required processes for requesting those images, and the image requests were cancelled in the end. And they never actually found out, they never took images of that shuttle to see whether there had been any significant damage that could have potentially caused the issue that we saw on re-entry. I talked about the fact that it had additional instrumentation and that it wasn't being replaced. there were several sensors that shuttle did have in place, and 55 had already failed at the time that she was coming back into the Earth's atmosphere on that particular mission out of 181 sensors. So there's some other examples of normalization of deviance. As I said, I'm going to go through a couple of these just to touch on what some of the key elements of that normalization were, and then I'm happy to move on to some of the questions. So I've talked about Challenger a little bit already. I introduced that idea to you of the Challenger one. It broke apart 73 seconds after launch. I think anybody that was around at the time certainly remembers this image that we saw of the actual shuttle exploding. So the O-rings on the solid rocket boosters had become brittle, and they'd failed due to the extremely low temperatures of the day. In fact, it was unseasonably cold in Florida the day of the launch. It was hovering around about 0 Celsius, and there was significant ice forming on the vessels as well. It was assumed that the temperature would not have that much of an impact that could lead to the O-rings failing. And it was assumed that it wouldn't have that much of an impact because previously it hadn't had that much of an impact. And in fact, the data they had was somewhat inconclusive to suggest whether it would have failed in those instances. There had been some instances in very cold temperatures where the O-rings had managed to hold. But there were other instances where they did see partial burn through had occurred past the O-rings, blow past the O-rings in warmer temperatures as well. So the data that the engineers were working on was incomplete. And that meant that when they were challenged on it, they were left trying to prove that the launch was unsafe rather than trying to prove that the launch would have been safe. And that's a really important aspect that comes out of the human perception on how we look at things. Are we trying to prove that something's safe or unsafe when we're actually doing things? Okay. The 1996 Gretley coal mine flood. Now, this occurred in New South Wales, Australia. It was an underground coal mine, and it was near some unused or disused workings of a previous coal mine. They hadn't been mapped very well, those previous workings, but it was known to be a flooded, disused mine that was nearby. And there was always a little bit of water that was getting into the Gretley coal mine. So it was assumed to be a wet mine. It was always assumed there was always going to be water. So it was ignored that there was water seeping into that mine. It was thought it was groundwater. It wasn't really an impact of the nearby disused workings that were flooded. During the course of mining that day, they actually broke through the wall into one of the disused shafts that was full of water, and that caused a massive release of water that flooded the Gretley mine, and 4 miners died in that particular incident. So the assumptions that were made here were really about the idea that it was a wet mine to start with. So water being present was normal. That was a normal situation. It wasn't then noticed that there was an increased amount of water that was present. The amount of water they were getting each day was actually more than it had been years ago. So they were starting to see an increase in the wetness. But the cognitive bias that played in here was that the confirmation bias was, but it's a wet mine, so we expect water. And tragically, as I said, we saw 4 miners lose their lives when that mine flooded. The Texas City refinery explosion in 2005, so 15 years ago, the overfilling of the raffinate splitter tower on startup that led to a loss of containment of hot raffinate that then exploded and killed 15 workers. Now, it was a regular occurrence on the restarting of that tower that it be overfilled above its high level, because the high level switch on that tower was actually only in the bottom 10 feet of the tower, and the tower was certainly much, much higher than 10 feet. So it was routinely overfilled on startup. And the reason for this was because the operators had experience of when it wasn't overfilled, they would sometimes have a low-level impact occur that would cause cavitation in the pumps. So in an effort to overcome that issue and try and anticipate that issue and prevent it, they would regularly overfill on startup. So again, they made the assumption and they normalized that overfilling was okay because it was done on all startups. And in fact, it wasn't the first instance of hot raffinate spilling out from that tower on startup either. But it was the first instance of a major ignition and explosion that occurred. So again, the idea of having a flammable vapor coming and liquid coming out of the tower had previously occurred. What hadn't occurred in the past was the ignition of that. So it was assumed it would be okay because it hadn't happened before. And this is one of the big traps about normalization of deviance. It hasn't happened before, so it won't happen now, is the assumption that's often made. Pike River coal mine, so another mining example. So there was a methane buildup in the underground mine that ignited, and that first explosion trapped 29 miners. Our methane was accepted as a normal issue in that mine. It was a high methane content coal seam, so people weren't bothered by the fact that there was high methane in there. What the organisation started to do, though, was bypassing the methane alarms. And the reason they were doing this is because they were often seeing high levels of methane, which were causing the equipment to trip out. This was an instance where there was a lot of pressure on budget, a lot of pressure to get the mining done, a lot of focus in that space. So the organisational pressure to keep mining was significant in this instance. And so the methane just became normalised. It was accepted that this is just, there's methane in this mine and it's okay, until the day it exploded. Now, the miners were presumed dead following subsequent explosions that occurred days later. They were unable to ever get to the 29 miners. They are still entombed in that mine. There is currently efforts to try and safely extract them, extract their remains. But that mine is still currently sealed off, I believe, simply because of its methane levels are too high. It is an incredibly methane-rich coal seam in that particular space. The DuPont Bell plant, where they had some toxic releases in 2010, so 10 years ago now we're looking. Now, over a 2-day period, they had 3 separate chemical releases. And there was an assumed false alarm in there, so they'd actually normalised, again, a false alarm. They'd normalised an alarm that they assumed was false. One of the situations here was that they actually had a bursting disc in a line, and they had an alarm to let them know if the bursting disc had ruptured and leaked any of the toxic substance through. And those alarms were very, very unreliable over a period of time. And so the operators had got used to not believing those alarms. They had assumed they were always false. What had actually occurred in the background was some replacement parts had been put in, and the reliability of those alarms improved significantly. So when they saw that they had this alarm, they assumed it was false because they'd become accustomed to it. Again, this is all down to our biases and our normalising what we see. They normalised that that alarm was always false. In this instance, that alarm wasn't false, and there was actually a release of a toxic substance. And there was a fatality of one worker as a result of this particular incident. So again, there's management of change that played out in this one. There's organisational communication and how well the changes were communicated to people, the training-related matters. But fundamentally, people were assuming things that weren't actually the case, and this is because they were normalising what they had seen over a number of years. And lastly, as an example, in 2012, you might remember the Costa Concordia cruise ship grounded and then subsequently keeled over, and 32 lives were lost in this particular instance. Now, this is an interesting example, and sometimes people challenge why I use this one to talk about normalization of deviance. And in fact, you could also talk about the organizational culture of that particular vessel as well. The captain was performing what was known as a high-speed sail-by. So the captain was navigating through in between an area where there were known rocks, and they were doing it at high speed. Because it's very dramatic for the passengers on board to see and for the people on shore to actually see it as well. They'd assumed it was okay because they'd done it before. They'd done it several times before. But if you just get it slightly off, you're going to run aground. And that's what actually happened this time. So they'd normalised what was in actual fact a behaviour that was not allowed by the Costa ship line as well as by the local port authorities. But they decided that it was an okay thing to do, and they got it wrong on that day. It wasn't the first time they'd ever done it, though. And so we need to remember that, again, this is a normalisation of a behaviour that is an unacceptable behaviour to have. And sadly, in that instance, 32 lives were lost as that ship then sank. So, in conclusion, the normalisation of deviance is a very dangerous human condition that we are all subject to. No matter what role we're doing, no matter how good we think we might be at doing our job, we are all subject to normalisation of deviance because we stop noticing what we see every single day. And that accepting of that normalisation, accepting of those deviances, it actually prevents us from seeing what the real issues are that we might have. So I think a question for us to all think about is, what can we do to combat this complacency? So I'm going to take some of the questions now, and I see we have quite a few questions come through already, so thank you very much for that. I'll start with the first question I have here is, does complacency have a role to play in human factors? And I think, yes, I think that complacency does, but we also need to remember that when we say complacency does not need to be a deliberate action. Sometimes we become, normalisation of deviance is an example of becoming complacent. We're not doing it deliberately, but it happens inadvertently in what we're doing. So we stop noticing that something is wearing down. We stop noticing an alarm that comes through. We just don't see these things anymore as we go through what we're doing. So it's always helpful to try and go out and see if we can change out that complacency a little bit by practicing some active thinking, I think, is an important part. And I think I've got some questions coming up that will lead to some of that as well. The next question, could we say that all is a matter of human behaviours? Human actions are the core of the failure? Well, yes, but we need to make sure that we don't just blame the humans, because the humans are doing things for valid reasons. Nobody sets out to deliberately cause an incident. What happens is sometimes we see instances where people make mistakes. We do see some instances of deliberate or willful behaviour that does occur, and that does need to be addressed. But where people make mistakes, we actually need to accept that humans can and will make mistakes. What we need to focus on is making sure that those mistakes are not going to lead to a catastrophic outcome. I think that's really the more important point here to think about. How do we make our systems and processes resilient enough so a human making a mistake doesn't lead to an incident occurring? And some of those mistakes can be quite simple things, and some of them could be significant things, but we need to try and prevent them being catastrophic in their nature. So the next question is, what should we do to avoid normalisation of deviance? So this is an interesting one. I think some useful ways might be, if you want to go for a walk through the plant to see what's actually happening, take someone that's unfamiliar with that area of plant or with that plant at all. Engage someone else and get them to ask you questions about what they're seeing, because they have a completely fresh set of eyes. They're seeing things from a totally different perspective, and that could be very helpful for you to understand and realise some of the things that you've normalised away. So I would suggest that engaging with people and having conversations and asking them to take a look will be very helpful to you to really help people understand what's going on at that point, and to help you see what some of those deviances are that you may have normalised. Someone has asked whether the slides will be provided. This webinar is being recorded and it will be uploaded to the IQME Safety Centre YouTube channel, as well as the IQME Safety Centre webpage, so you'll be able to review that webinar at your leisure. How did the ignition take place that overfilled the raffinate from the splitter tower? So that particular ignition source was actually thought to be a utility vehicle that had its engine running that was parked in the vicinity. The engine, it was a diesel, it did start to run on. They tried to turn the ignition off and they couldn't turn it off. They then fled from that scene, and it was believed to be perhaps the hot engine that caused that ignition. The Chemical Safety Board in the US has some very detailed investigation reports, as well as a fantastic animated video about that particular incident. So if you go to www.csb.gov, you will find details on that incident there. Someone else, it seems like the reason underlying is cost saving and KPI driven. For example, the flight trip in the case of the space shuttle. Yes, there is certainly an impact here that business pressure that is put on organisations will lead us to look for expedited solutions at times, and that can lead to normalising some of the things we see. That's why it is always important to make sure that we are trying to focus on proving the safety of things rather than proving that something is unsafe. So it is a particularly important area. A number of those examples I gave you did have some direct cost or schedule causes associated with them. Someone has said, from my experience, we still see similar incidents even at present. Aren't we learning the lessons from the past? It seems that they're not successful. Sadly, I think you are correct in that. I don't think we do a very good job of learning from past lessons. I think there's a whole range of potential different reasons here. One of them, I think, has to do with what we call hindsight bias. When we know what the cause was, instead of taking the opportunity to think about how we might prevent it, or indeed be willing to accept that we could make that same mistake, we often fall into the trap of justifying in our own minds why we wouldn't make that mistake. And so that certainly has an issue associated with it. I think there's a lot more work that needs to be done in improving lessons learned, and I think the fact that I've had 145 odd people on this webinar is testament that there are people out there that want to learn. So we need to keep providing useful information, but look at maybe how we provide it. Can we provide it in a better way for people? Someone's asked, how do we detect the alarms that are false or alarms that are actual to avoid normalisation of deviance? Well, this all comes down to your reliability and maintenance strategy. If you have alarms that are critical, then how are you looking after them to make sure that they are reliable when they need to be giving you the information? So you really need to focus on making sure that you have reliability in your equipment that you're relying on. And if you have a whole lot of alarms that are not critical, if they're detracting away from the operator doing the job, then why do you have them as alarms? You really only should have an alarm where there has to be an absolute action taken within a certain time frame. So look at your alarm rationalization, make sure you don't have too many, and make sure you maintain those alarms so that you understand the reliability and the failure mechanism and the failure rate of that type of alarm. That's all you can do to try and prevent normalization of people assuming false alarms. There won't be any certificate provided for attendance to this webinar. We don't tend to do that for these sorts of webinars. Are there any strategies or best practices one can apply to eradicate unacceptable normalization of deviance behaviour? So really it is around trying to test your assumptions, test what you're seeing in your assumptions, and engaging with other people. As I said, bring people in to look at your organisation. Might be an operator from another facility or an operator from another part of the plant or an engineer from another part of the plant. Bring them in to look at what you're doing. This is all part of assurance and auditing as well. Auditing should not be seen as the audit police coming to check up on you. It's actually a great opportunity to uncover where you might be becoming susceptible to normalization of deviance. So embrace auditing in that positive way. They might find something that's going to be helpful to you to prevent your next incident. So that is really important. The next comment is, I guess leadership also sets the tone to avoid unacceptable normalisation of deviance. Absolutely it does, yes. The culture that the organisation is willing to accept comes down to the leadership of the organisation and what work they are willing to do to try and prevent incidents occurring, to try and make sure that people remain alert, that they don't just accept what is obviously not right, that things are challenged. Leadership is always key in everything we do in process safety. I've done a number of webinars on leadership recently. They're on our YouTube channel, and they are absolutely vital in making sure that we get the best outcomes in our organisation. Leadership is very much an undersold thing from a process safety perspective that we really need to be focusing on. If there is a design error on process equipment or inspection error, shall we call it human error or accepting deviation? Well, humans are involved in all of these things. It's not actually about determining it as human error. Saying something is a human error doesn't help you fixing it. You need to understand why the human made the error. What was the human factors elements? What organizational factors, what task factors, what personal factors led to that error? Determining that something was human error should never be the ending point of an investigation. That's actually really the starting point. Why was the error made? What is the reason here? That is far more useful to find that solution for. What would be the most effective approach to avoid or prevent normalization of deviance? As I said, I think it really comes down to your assurance aspects and engaging with other people, checking what's going on and what you can do to try and improve, and try and see what you no longer see anymore. You need fresh eyes to do that. So that means you need to bring other people in to take a look. In some instances, it may mean that you need to not continue to be that person in that role anymore. The role might need to go to someone else so they can see what you no longer see anymore, and you move on to a different role as well. As process safety professionals, we should spend more time in understanding at-risk behaviour and how we can influence it, i.e. spending more time in understanding human error and planning for it rather than ways to try and design it out. I think there's both parts to this. We do need to focus on trying to design our systems so that it's as easy as possible for the human to get it right, rather than making it easy for the human to get it wrong. And I think that's a really important thing. So that does come into the design aspect. We should be trying to design so humans, if they take a shortcut or if they get it wrong, it's going to work out okay for them. We also need to understand why someone has made a mistake. There will be systematic, organizational, personal, or task-related factors that led to the person making that mistake. You need to understand what they are first. Then you can address those. So saying that the operator failed to take the sample, why did the operator fail to take the sample? The fact they failed to take the sample is actually not that important because we can't fix that. But what we can fix is the underlying organizational reasons of why they didn't do it, for example. And that's really the conversation, the point we need to be getting to in this human factors and human impact area. Could we reduce the human deviations instead of just mitigating the consequences? Well, that I think really comes down into part of that design. How can we design to get it right rather than to get it wrong? So an example I use in human factors here of a design to get it right rather than to get it wrong. When automated teller machines were first invented, they had a very logical sequence to them where you put your card in, you put your PIN in, and you got your money, and you could then go away. And they had an ongoing situation of people leaving their cards in the machines because they'd achieved their outcome. A small logic sequence change prevents people leaving their cards in the machines now because you put your card in, you put your PIN in, you get your money, you get your card back. So you get your card back, then you get your money. So by forcing you to take your card before you've achieved your outcome that you're looking for, the money, it holds you there. So a simple change in the logic, a design change, actually reduced the human being able to get it wrong. And that's what we need to be thinking about in our processing plants. How can we try and avoid the human getting it wrong in the first place? How do we effectively measure and reflect the success story of human performance for future endeavours? Wow, that's a really tough question. There are a range of different metrics I think that we need to be looking at, particularly in the leading side of process safety around human performance. There is a lot of work done by human factors experts, and I certainly do not claim to be a human factors expert. I have a very rudimentary knowledge of this field. You need to be engaging with psychologists who specialise in this field, and they will be able to do things with you, such as task analysis, to see where the key aspects are and what needs to be done. So you really need to be focusing on dealing with some of those sorts of issues and measuring human factors in that way. And there are some quite effective ways that human factors specialists and practitioners can actually help you in measuring in that space. Someone's noted that the utility vehicle should have had a spark arrestor. Yes, but that wouldn't have actually dealt with the fact that if you've got the utility vehicle in a flammable area to start with, and you've got a large vapor cloud, a hot surface might be enough to ignite it. You don't necessarily need the spark. The point here in that incident is more about the normalization of overfilling, leading to a release rather than where the ignition source came from. The ignition source was obviously important in this, but if the product hadn't been released, then we wouldn't have had an explosion in the first place. So make sure you really go right back in the chain of events when you're thinking about an incident. Can I suggest a good book or any material discussing the case studies of process safety disasters or material for safety studies? Anything written by Trevor Kletz, Kletz, is very good. He's written some good books called What Went Wrong, Still Going Wrong, Lessons from Accidents. All three of those books are very, very good in helping you understand some of these things, as well as The Challenger Launch Decision by Diane Vaughan is a great book to read. Professor Andrew Hopkins has written a number of books on some of these aspects as well. So anything by Professor Andrew Hopkins is a good one to read as well. There's a range of different book resources out there that you can certainly take a look at there. Based on my experience, which is the most vulnerable areas in a process plant where human factors play a major role and often lead to catastrophic events? I'm not sure it's really about the major areas. I think you need to, if you're in a processing plant, think about how you can lose control. It's all about losing control. So whatever you focus on, you need to focus on maintaining the control of your system, of your process. When you start to deviate outside of your normal operating envelope and outside of your envelope of control, that's when you're going to have a problem. So I would focus it on what does a loss of control look like in all areas of your plant, and you then need to do a detailed risk assessment to understand what the consequences could be here, and that should then feed into what risk treatment you need to take in implementing controls to prevent or mitigate that particular incident. What management measures are required to avoid normalization of deviance? Auditing and assurance activities are really important here. Being open to the data and trying to deal with biases. So if you've got confirmation bias, then you may only be looking for information that confirms what you already assume. So you need to be focused on trying to deal with those sorts of biases in your investigation activities as well. What's my take with regard to the future towards more AI, digitalization, and technology application in the future? Will this help us for a safer environment or otherwise? There is an enormous amount of fantastic work that's going on in this space, and big data has the potential to tell us all sorts of different things that we can't currently see in the way we look at things at the moment. However, we need to make sure that when we're applying technology, we're applying it because it's the right thing for that problem. Applying technology for the sake of it because it's cool and it's brand new does not necessarily give us the outcomes we're looking for. And don't ever think that simply because we are applying technology that we are eliminating the human element, because we don't yet have a true AI that is capable of creating itself, which means a human has created it. A human has built it in some way. A human is maintaining it. A human is operating it. There is always a human involved at this point in time. So we need to make sure that we understand what's going on from that perspective and how we can adequately monitor and deal with the human aspect in that particular area. So, you know, we can always assume that if we're going robotics or animatronics, that we're removing the human, but at the end of the day, it's the human that's actually creating these things. Therefore, the human is still well and truly embedded in that process, and the human is still capable of normalizing some deviant behavior in some way. We need to identify the systemic root causes in order to make a difference. Blaming the human is just lazy. Incident investigators need to identify how the system led to the operator making the mistake. I cannot agree with you more. The fact that we make mistakes is human. What we need to figure out is what led to that mistake. What were the systems that allowed that mistake to happen? That's something we can actually address for improvement. Normalization is already a global issue within the COVID-19 measures. Is there a path where IQME can assist with this kind of example you have shown today? That's a very good question, and something I'll think about what we can do, because you're right. I'm currently sitting in Melbourne, Australia, which I believe at this particular point in time has the world's most drastic lockdown measures on it, as we approach our nightly curfew, in fact, even. And we've had to go to this level because people have become complacent. We've normalised the risk. We've become complacent, and that has created issues in dealing with the global pandemic from the Victorian and the Australian perspective. So I'll have a think about what we can do in that particular space. There may well be something we can do in that area. Someone has suggested a podcast by Professor Todd Conklin, Pre-Accident Investigations. Yes, actually, that is also really good. That's a great suggestion. Thank you for the person that wanted to know whether there were any useful books or anything that they could take a look at. There's also a lot of great work by Professor Eric Holnagel on safety too, and looking at the efficiency thoroughness trade-off that we do every day. And that's also part of normalizing things. We trade off on the good things and some of the not so good things. So we might take a bit of a shortcut because it's never been a problem before. That's normalization of deviance, and we do it in our everyday life. It is, in fact, human nature. So we need to be challenging ourselves to make sure that we can deliver the outcomes that we need to be delivering, so we don't end up with the sort of incidents that I've talked about today. I think they are all of the questions. Someone else has made a comment. Brilliant, much appreciated. I had not heard of normalization of deviance before, but it seems an excellent description for this phenomena. Yes, it was Diane Vaughan, I believe, that first defined it in that way, and it's certainly now been quite a useful terminology that we use. Someone else has suggested a book by Professor Sidney Dekker, The Field Guide to Human Error Investigations. Again, also another very good book on really getting to the bottom of why the human did what they did. Because at the end of the day, that is a far more important piece of information than what the human actually did. We've been working in trying to deal with some of the hindsight bias in the Safety Centre for a number of years. And that's the basis of our case studies that we've developed, where we don't tell you what the incident is. We give you all the context and the situation going on and then ask you to make decisions based on it. And what we see in that space is often people will make the same decisions if we give you the same triggers, the same context. So we remove the idea of you thinking, well, I wouldn't make that same mistake because I'm better than that, I'm smarter than that, or whatever it is. We actually put you in the situation and show you that you can make that same mistake. It can be quite an eye-opening and shocking thing for people to see. Great presentation. Do you have a view on the issue of aging equipment and the effect of equipment obsolescence in managing process safety? Feels to me that cost issues will increase exponentially in the couple of years as we recover from COVID-19. That's a really good point and a really good question. And, you know, I've worked in facilities where we actually at times would be on eBay searching for certain parts for equipment that was becoming obsolete because you could no longer buy it from the supplier. This is a real safety issue that we have, and we need to be careful that we don't stumble into not maintaining because we can't get the parts, but not upgrading because, well, it's still working okay. We need to try and avoid that trap, and that is a significant potential. And I think as we do recover out of COVID-19, we are going to see a lot more economic pressure, and I think we're going to potentially see a lot more process safety issues from that. So we need to be hyper vigilant about all of this going ahead at the moment. Someone else has commented that Amy Edmondson on psychological safety is a good person to follow to understand the human aspects too. Thank you very much for that. And how do we stop management just wanting to fire or sack the people who make the mistakes? That's a really tough question, and it's actually about organisational culture and leadership. And it needs to come down to really good leadership activities with people. So our leaders need to actually understand some of these aspects. We need to be educating them. Sometimes that education will need to come external because they won't hear it from people within their own organisation. It's a journey, and it's a cultural maturity journey that organisations have to go through, and that's where we actually end up having to focus in that particular area. So thank you very much, everybody, for your great questions. I hope you enjoyed this webinar. As I said, this webinar has been recorded and it will be made available on our IChemE Safety Centre YouTube channel. There's a number of other webinars on that channel, and I'd encourage you, if this is your first one, to go and take a look at some of the other webinars that we've been running. We will have quite regular webinars for the next certainly a couple of months at this stage, well into September. We have them scheduled already. We've got some great topics coming up for discussion, so I look forward to you joining me again at some point in the near future. I wish you all a very safe day, and please take care, be well, and I look forward to engaging with you again in the future. Thank you very much and goodbye.